All right, so we are very happy to have Siqi Liu with us here today, even though she is joining remotely. So Siqi is a postdoc at DIMAC/IIS, and she has done some immensely beautiful work on high-dimensional expanders. She has been trying to understand this area deeply, HDXs, coding theory. She has been thinking about constructions of HDXs, like probabilistic constructions and whatnot. And that's what she would be telling us about today. So over to you, Siqi.
Yeah, thank you. Yeah, thanks to the organizers for inviting me. And though I'm not in there in person, so it may be a little bit hard for me to pace the talk. So feel free to ask questions in the middle if you want to slow me down or something is unclear. Yeah, please feel free to interrupt me. And today, I'll be talking about detection and recovery of latent geometry in random graphs. And actually, this is remotely connected to high-dimensional expander constructions, but I won't be focusing on that part, the construction part today. I'll be talking about some basic questions related to detection and recovery on random geometric graphs. Okay, so let's jump right in. So the model we'll be looking at in this talk will be random geometric graphs. This was first studied in 1960s by Gilbert, and the model they studied at that time was called the Gilbert's disk model, where essentially on the rail plane, one samples through the Poisson point process endpoints, and then among these endpoints, you connect the 2 points x and y if their Euclidean distance is at most some threshold r that's being picked ahead of time. And this way you get a graph. So this graph itself, when forgetting all the geometry underlying it, just take the graph. This will be the geometric graph. And this is one model for generating random geometric graphs. And it can be more generally generalized to other metric space, x, comma, d, where x, we just think about them as a set of points from some space, from some manifold or anything. And d is a distance function that gives pairwise distance for points inside x. And then it also comes with a measure mu on the set of points x. And in general, the procedure of sampling a random geometric graph is one sample n IID points from this distribution mu and connect the 2 points x and y, or vi and vj, if their distance is at most r under this distance function that we give. Okay, so this is the model. This problem has been studied for a long time, and people have been studying questions like the giant component size or percolation threshold and chromatic number and so on. Many of the low-dimensional space, such as cubes, low-dimensional unit sphere, torus, and compact Lie groups. Penrose has a very nice textbook called Random Geometric Graphs that summarizes many of these cool results. And in more recent years, there are more study of these of such random geometric graphs in higher dimension due to their application and connection to network analysis and biological networks, and also topological data analysis and so on. So, so that brings us to the main focus today. So in the rest of the talk, I'll be talking about some recent developments on the question of detecting geometry in random geometric graph, specifically over the unit sphere in d dimension. But here we're not thinking about d as a constant, but rather as a growing function. And also we'll next be talking about, and after that we'll be talking about some recent developments on the question of recovering the geometry in variants of this random geometric graph over unit spheres. And we'll conclude with some other open directions. So just to explicitly state this model we'll be focusing on, we'll be considering the random geometric graphs over the unit sphere in d dimension. So just to recall, the way we sample is we sample n IID points on the unit sphere in d dimension and call them v1 through vn. And we connect vx and vy if and only if they're close in Euclidean distance. But somehow in this literature, I guess the more canonical way people say is we take the inner product of X and Y and only connect the two if their inner product is larger than some predetermined threshold tau. And this tau is determined by both the parameter D and the edge density parameter P. So this is the average probability of an edge exists between two random points on the sphere. Okay, so yeah, and something we want to note is that essentially if we fix P and it brings D to infinity, this threshold tau will converges to 0. So one matrix that I want to define here is the so-called Gram matrix or the inner product matrix, which is defined as VV transpose, where V is the matrix whose rows are essentially VIs, the coordinates, the vector of the matrices of the vertices that's being sampled in this process. So VV transpose, its XY entry will just be the inner product of VX, VY. And then we know from the definition of this model that the adjacency matrix of the final graph that we obtain is simply applying a threshold function on this VV transpose, where the threshold is given by tau. Okay, so this is the model. And yeah, okay. In the rest of the talk, we'll use this notation GNPD to denote this random geometric graph over unit sphere in dimension D with edge probability P. Okay, so the first question we'll be considering about this random geometric model, I guess it's a very natural question. That is simply, when could we detect the underlying geometry of the graph? Namely, we know that we're given a graph that's being generated from a unit sphere. But when we forget about the information of the vectors, we're only given a graph. Can we still tell that this graph is actually coming from a unit sphere rather than coming from some model in which the edges does not have any dependency? Okay, so to be more specific, we're interested in the question of distinguishing between two random graph models. The first one is the random geometric graph that we just described. The other one is the Erdős-Rényi model, GMP model, in which the edges simply does not have any correlation. And the question is, when can we distinguish between the two models? Here I want to make a comment that we are curious about, for different choices of P, what dimension D, for what dimension D will we be able to distinguish between the two models? So we're thinking about D as a function of N and P, starting from this point in the talk. We can think about that when D is really small. For example, let's say even D equal to 2. Essentially, we'll just have a circle in R2. If we sample a random geometric graph over this model, let's say P is not too big, then essentially what we get is a noisy cycle. That's what we get as a graph. And we can imagine that's going to look very different from a random Erdős-Rényi graph, because that would not look like a noisy cycle in any way. As a result, we can see that when D is really small, we can easily distinguish. And it turns out that when D is really big, what happens is that if we sample two random points from a unit sphere in very high dimension, the 2 points distance concentrates very well. And as a result of that, what happens is that essentially the random geometric graph would look very similar to a random Erdős-Rényi graph. So when D is really big in terms of N and P, it's going to be very hard to distinguish. So that's kind of the intuition. And let's look at some of the known results on this question. So this problem, as far as I know, it's first studied by Bubakdin and Eldon Racks in 2016, in which they studied precisely the question of when can we distinguish efficiently between GMP and GMPD. what they show is first that when D is sufficiently small, there exists an efficient algorithm that distinguishes between the two with high probability. So by small, I mean D is smaller than the binary entropy of P raised to the power of 3 times n cubed. And the algorithm is really nice and efficient. Essentially, what it does is it takes adjacency matrix and center the matrix by subtracting P, the average edge probability from every edge entry. And then in this new recentered graph, compute the number of triangles, weighted triangles in this graph, and apply a threshold to it to check whether it's from a Sreni graph or from random geometric graph. The intuition is that because of the underlying geometry, we kind of expect many more triangles in the random geometric graph than in the random Sreni graph. Because in a random geometric graph, if we know two vertices V1 and V2 are connected with each other, and V1 and V3 are connected with each other, we know that these kind of checkmark shape exist, then very likely or more likely than before, V2 and V3 would also be connected because they're both close to the point V1. So because of that intuition, there would be more triangles in this case in the random geometric graph, and therefore triangle counting is actually a good distincting algorithm. And actually, it's later proven by Bangachev and Bressler that triangle count is the optimal low-degree polynomial function that can distinguish between these two random models. Okay, and furthermore, in this Bubak Ding Rex paper, they also prove a information theoretic result in which they say that when D is sufficiently large, in particular when D is much bigger than n cubed, then it's information theoretically impossible to distinguish between the two models because their TV distance vanishes. So in particular, we can note that if P is a constant, so if the edge probability is constant and it's a very dense graph that we're considering, then essentially n cubed is the correct threshold for distinguishing. So if D is smaller than n cubed, we can distinguish, and D is bigger than n cubed, we cannot distinguish. But for smaller P, there's still a gap between the algorithm, efficient algorithm, and the impossibility result. In particular, in this paper, they proved this impossibility result, this TV distance vanishing result, by showing that actually if you take the inner product matrix VV transpose of the random geometric graph, it actually converges in this regime of D, converges to a shifted Gaussian orthogonal ensemble. So this is a matrix with ID Gaussian entries. Therefore, a symmetric matrix with ID Gaussian entries. Therefore, essentially, you lose symmetry when D is, you lose correlation between edges when D is bigger than n cubed. But intuitively speaking, you may think that this is asking for too much because this is asking the inner product matrix to be indistinguishable from something, from some like ID matrix distribution. However, we simply really just need the adjacency matrix to be indistinguishable. And applying threshold function may already lose some information about the original thing. So potentially we can get a slightly smaller lower bound on D for indistinguishability. And that intuition, yes.
So in the lower bound, what is the dependence upon P?
This lower bound does not have a dependency on P. So like it's literally D much bigger than n cubed.
And for any P, the total variation distance.
Yeah, for any P's, yeah, that's right. For any P between 0 and 1. Yeah. So yeah, that's another kind of indicator that maybe this is not a tight correct threshold that's getting. And this is indeed confirmed by a later improvement by Brendan, Bressler, and Nagaraj in 2020, in which they improved this threshold upper bound, actually. But okay, like they improved the information theoretic side of the bound, and they in particular show that a lower bound of D is bigger than the smaller of these two. You can see that both of them are better than n cube. So, okay, I guess this is always better than n cube, and the second term is better when P is small. So if we actually look at a couple choices of P, we see that in the relatively sparse regime where P is, when the average degree is at most polylog n, this improved the lower bound n D from n cubed to n to the 3/2. And also improved when the average degree is a small polynomial. But of course, in the dense regime, it didn't change things much. It improved the constant in front, but yeah. Okay, so they're able to achieve this improvement precisely because they actually don't look at the inner product matrix, because the inner product matrix threshold was actually the one given before. What they did in this work to improve is that they treat the graph distribution as a distribution on n choose 2 indicators of whether a specific edge xy exists in the graph or not. So now we're essentially looking at the TV distance between a n choose 2 random variables. And recall that in the Erdős-Rényi graph, this is just n choose 2 Bernoulli random variables. And what they did is they found the KL divergence between these two distributions. Nice thing about KL divergence is if one of the distribution is a product distribution, then the KL divergence factors. And essentially, it suffices for one to prove that the conditional distribution of the more complicated distribution is going to, with high probability, look like the Bernoulli distribution. So specifically, in this example, it just says that if for a typical random geometric graph, in which I know everything about the graph but the existence of edge 1 and 2, now I look at the conditional probability that 1 and 2, the edge 1, 2 exists conditioned on all the rest of the graph, all the other edges, then the distribution of this edge existing is very close to the Bernoulli distribution P. In fact, we want it to be little o of 1 over n squared close because we'll incur such a loss in every single random variable, and they're an order n square variable. Okay, so they were able to improve the result because they're looking at KL divergence for this specific distribution. Okay, and later in a joint work with Mohanty, Shrem, and Yang, we further improved this lower bound to h square n cube for all choices of P. In particular, if we look at it in different density regime of P, in the relatively sparse regime, we improved it from n to the 3/2 to n. And we also improved, basically shaved a square root n in all, like in the sparse case and relatively dense case. But I think what's more interesting is that we were able to do an even better improvement in the case when P is really sparse, when P is really small. In particular, when P is on the order of 1 over n, we're able to improve it, the lower bound to simply like log to the 36n. If you recall, the upper bound, well, the algorithmic bound for this case, P is on the order of 1 over n, actually would tell you that when D is much smaller than log cube n, one would be able to efficiently distinguish. And now we're able to say that when D is much bigger than log to the 36n, it's impossible to distinguish. And we're able to achieve this by looking at yet another different distribution. Now this distribution we're looking at is no longer a distribution over edges, but we instead look at n random variables, with each random variable associated with a vertex vi. And the random variable indicates the set of neighbors of the vertex vi among the first I minus 1 vertices. So this gives us a distribution over n random variables. And we're going to still use the fact that the corresponding distribution in the Erdos-Renyi graph would be n independent, although not identical, but independent random variables. So on the Erdos-Renyi graph, it will be the product of a bunch of binomial distributions. Well, on the random geometric graph side, this will be some complicated distribution of neighbors. And we're going to still just look at the conditional probability that for example, the nth vertex condition on the random geometric graph already constructed over the first n minus 1 vertices. What is the distribution of the nth vertex neighbor among the first n minus 1 vertices? We're going to look at this specific conditional distribution and see how far away is it from this binomial distribution of binomial n minus 1 comma p. So next, I want to spend a little bit of time trying to give you some intuition and a proof sketch of essentially this result in the sparse peak case. Any questions so far? Okay, I will continue then. So yeah, essentially here we already see in order to understand when the TV distance vanishes in the sparse regime, it boils down to understand when this distribution of neighbor of the last vertex is actually very close to a binomial distribution. So let's see how to generate this distribution first. So to generate this distribution, we are first given a geometric graph Gn minus 1, just a graph. And what we're going to do is we're going to do a rejection sampling points V1 through Vn minus 1 on the unit sphere, condition on the fact that their geometric graph is this exactly equal to this graph Gn minus 1. And after that, we can draw a circle, or draw a sphere cap around each of these vertices Vj. The sphere cap has radius like square root 1 minus 2 tau, which essentially means like if a point lands in the sphere cap, then it will have an edge connecting to the center of the sphere cap, to the vertex correspond to the center of the sphere cap. So the sphere cap is just saying like everything land in the cap is going to be a neighbor of this vertex. So okay, so these points, we can draw sphere caps around them, and these sphere caps partition the unit sphere into at most 2 to the n minus 1 sets, and each set, well, I guess 2 to the n minus 1 shapes, and each shape really is indexed by a subset of vertices. Let's call it S. And this shape's relation with S is just that this shape is equal to the intersection of all the sphere caps of those vertices inside S, and the complement of the sphere caps for all those vertices that's not inside S. So that is to say, like, essentially, when I sample Vn, if it falls in that shape, its neighbor will be exactly equal to S. Okay? So essentially, the distribution of the neighbor of n is really just for us to understand what's the distribution, what does the size of this shape look like? What's the area of this shape on the sphere cap? And we know that the area, the size, the volume, or the area or the volume of this shape actually primarily depends on the location of these VJs for all J and S. I want to say that, of course, it also depends on the location of all the VIs that's not in S. But those dependency is very tiny. So primarily, we just simply need to look at really for a small subset of S, what the distribution of Vj for J in S would look like in this conditional distribution. Okay, so yeah, so here we established that to understand the probability of neighborhood equal to S, it boils down to understand the probability that condition on this random geometric graph over the first and -1 vertices. What's the vectors distribution for Vj, the joint distribution of Vj for J in S? And the hope is that the real hope is that in order for the neighborhood of N to follow this binomial distribution, we would really want the Vj's to distribute uniformly and identically over the unit sphere. Sorry, not identical. Uniformly and independently over the sphere. Okay, that'll be our goal. Because if that's the case, then their sphere cap size is essentially going to be roughly p to the power of s, which is pretty much what we would want eventually in order to prove that this distribution of neighbor is very close to binomial distribution. So that's what we're going to do next. Okay, so when is this true? So when is the Vj is going to be ID uniform on the sphere? Well, it turns out that we need two things. And the first thing is we want this Gn-1 to be locally tree-like. This is really satisfied when our edge probability is very small, right? Because when our edge probability is very small, we can actually decompose the graph in a way similar to the one on the left. So let's say our set S consists of V1, V2, and V3, 3 typical points in the graph. And because it's locally tree-like, we can draw a small tree around each of the V1, V2, and V3, and they will be disjoint. And removing all these trees will still be left with many edges and many vertices in the rest of the graph.
Siqi?
Okay.
Siqi?
Yeah.
So I have a kind of a naive question. So here we are conditioning the fact that Gn-1 is a geometric graph. So even after this conditioning, can I claim that Gn-1 is locally tree-like?
With high probability. Not always, but with very high probability is enough for us.
That's what I mean. So with high probability, is it still...
It's true. Actually, I kind of hide why, because one can prove that random geometric graph is actually sandwiched between the trendy graph of slightly higher and slightly lower edge density. And then you can just derive its locally tree-like from the fact that it's dominated by some random geometric graph. Some Erdős-Renyi graph.
And when you say it's sandwiched between two Erdős-Renyi graphs, what does that exactly mean? It contains some Erdős-Renyi graph as a subgraph with high probability and is contained inside another one.
Yeah, exactly. You can couple them. You can couple the three distributions.
Okay, perfect. I see. Yeah. Okay, thank you.
Yeah, that's an important point. Yeah. So right, because of that, we actually can decompose the graph look like that for a typical set of S. Okay, because of that, it's relatively straightforward that then V1, V2, V3 should first be independent from each other, because once we already have this kind of decomposition, what we can do is we can just first sample the vectors for all the vertices, all the blue vertices in the middle here. And then we know that once we have all their vectors, essentially the distribution of V1, V2, and V3 only depends on the leaves, on the vectors we assign to the leaves of these trees. Okay, that's not precisely true, because the fact that two vertices does not have an edge in between them kind of provides some information. But I would say those information ends up not being very important. So essentially, when you just condition on the roots of these three trees, then the distribution of V1, V2, and V3 would essentially be independent from each other. So that's the independent part. And then the uniform part, to prove that each of them also is roughly a uniform distribution, we would need requirements on the dimension D, and also with the correlation decay phenomena in these kind of random graph models. So precisely what's going on here is, so the correlation decay of a vertex V in this random geometric graph is saying like, condition on we know the vectors for all the roots, for all the, sorry, not all the roots, all the leaves of the tree. Then condition on these assignments, the vector that we assign to V, to the root of the tree, is going to be upper bounded by something. And that something is just saying like when our dimension D of the sphere is large enough, then this distribution of V conditioned on all its leaves will essentially still be uniform. So because of that, we actually are able to conclude that if we pick D large enough, and in the particular case we're considering here, we pick D to be bigger than log to the 36n, then what we end up getting is that all these VJs from S are ID uniform on the unit sphere.
So Siqi, just confirming here, L denotes the number of leaves or
the depths of the tree.
The depth of the tree, right? Okay, okay.
The depths of the tree, yeah, but I guess I was trying to ignore it, but L is the depths of the tree. Yeah.
Okay, and like this 1 over square root D dependence, how does that emerge? The 1 over square root D, the total rotation distance, the bound that you claim is total of 1 over root.
This kind of emerged from the definition of this model. I couldn't say too much about it, but let me think. Is there any intuition I can give? I think it will get clear if actually one look at what exactly the threshold tau, the correlation between two adjacent vectors would look like. It turns out that if you've picked P to be on the order of 1 over n, then like the tau will be roughly 1 over square root T.
Okay, okay.
So that comes from there. But I couldn't give much more intuition without saying.
Fair enough. Yeah.
Yeah.
Okay. Thank you.
No problem. Yeah, thanks for the questions, actually. Okay, so essentially this finishes the entire proof. It's just saying the log 36 comes from that we want this correlation decay to show up in our calculation. And the reason we can only do this improvement for very sparse regime is because in the sparse regime is where we can actually get this locally tree-like property. So, but this argument doesn't quite work for the dense regime. But yeah, so, okay, so I guess I want to summarize so far what's already known about this model. So so far what's known about this model is we have for different density regime of P, polylog average degree, polynomial average degree, and order of n average degree. We have the string dots, which is the threshold up until which we know that we can detect using this triangle count argument, algorithm. And the red dot is beyond which we know that information theoretically we cannot distinguish between the two models. And we see that in the relatively sparse regime and relatively dense regime, we still have a gap to be closed. And yeah, these are the open questions, and I think new ideas would be needed to close things in these cases, especially in the relatively dense regime, in which we know there's a polynomial gap between the two. So that'll be something to explore further. So that's the first open question. And now we switch gear to the recovery question. So the recovery question is essentially when we're given a graph, can we recover the vectors for all of these points? But because we're considering a random geometric graph over spheres, so everything is rotationally invariant, So essentially, we don't need to recover the exact labels of these vertices. We just need to recover the inner product matrix. That's the best we can do. So can we recover the inner product matrix up to some accuracy? Okay, so in order to do that, I want to introduce a related model called a soft random geometric model, because the recovery problem were first studied in these kind of models. So so the soft random geometric model is a model where the graph is not deterministically determined by the labels v1 through vn, but rather after you have v1 through vn, you're still like there's still some randomness in what the graph would look like. In particular, we're given a connection function rho that maps the inner product value to a another value, to a probability parameter between 0 and 1. And also this is a strictly increasing function. So, and then we connect the 2 points Vx and Vy with probability equal to rho applied to the inner product between Vx and Vy. In particular, if the inner product is really big, then this probability of there's an edge present would be big. If it's very small, then there's an edge present will be very small. Okay. So this is a softer version because there's randomness on top of the choice of V1 through Vn. And we still use P to denote the average edge probability of 2 random points on the sphere. Okay, so from this we can talk about our soft model, which is n rho d. P is hidden because P is already defined explicitly by this rho. Okay, so this is a soft model, and people have studied the weak recovery problem on soft model. So what does weak recovery mean? The weak recovery just means that when one is given the graph G, the algorithm, there exists an efficient algorithm and a constant epsilon, such that the efficient algorithm would output a guessed inner product matrix X prime, such that its distance, its Frobenius norm from the actual inner product matrix is bounded by epsilon n squared. Okay, so it's better than random guess. That is to say, and for this kind of requirements, for this kind of like weak recovery problem, Araya de Castro and Aldana McLinser-Peters have studied this problem, and specifically they showed that they consider the case when D is bounded, so like the dimension of the sphere is constant, it's a bounded constant, and they additionally require the function rho to satisfy some niceness condition that I'm not going to specify too much here. And if one assume that, they prove that essentially weak recovery is possible for bounded D and some nice choice of rho. In particular, the algorithm they're looking at is actually quite straightforward. What they do is they just take the adjacency matrix A prime. They take the adjacency matrix A of this input graph, and then they project it onto the top D dimensional eigenspace of A. Therefore, they get a matrix, and then they just rescale the matrix properly to get this output X prime. The reason this works is roughly the following. Under proper assumptions on this rho, the top D eigenspace of A, sorry, I think I mistakenly wrote this as A prime, but these are A. So on the top D eigenspace of this A, it's roughly actually equal to projecting the matrix, the related matrix, which is just applying rho to the inner product matrix itself. So this is actually the edge probability, sampling probability matrix. So when you project this other matrix onto the top D dimensional space, it's roughly equal to projecting just the adjacency matrix to the top D dimension. So this requires something about rho. And then the next step that's that kind of comes from like doing spherical harmonics is that if we just project this matrix of applying rho to the inner product matrix, what we end up getting is just a ray scaling of the inner product matrix itself. It's very important that we project things on the top D dimension. And what we end up getting is just a rescaling of roughly the rescaling of the original inner product matrix. And because of that, we can simply roughly recover the original inner product matrix. So that is the algorithm. Okay. And there's also recovery done in other random geometric models. But here, when I say recovery, I actually mean like the stronger version of recovery. Here, when I say stronger version is that we can actually recover the inner product matrix with the X prime such that their Frobenius norm is bounded by little o of n squared. So better than epsilon times n squared is actually little o of n squared. So much better than just random guessing. One can achieve this on this related model called the Gaussian mixture block model. This is a result by Li and Schramm in 2023. What happens in this model is that one just takes a mixture of two Gaussians and sample points from it, and then still like set threshold so that the average edge probability is P for two random points, and generate this resulting graph from it. So it's like a kind of a two community Gaussian mixture model. And then the question is still to recover the distance or the inner product. Well, actually here is more like distance, the distance matrix from this graph. And they were able to show that actually when D is much smaller than n times P, this recovery is possible. And they use very similar technique from before. It's a fully spectral algorithm, just using the top eigenspace to extract information about the inner product or about the distance between vectors. So this is a related model. And I guess another related result in the recovery regime is that Eldam, McAllister, and Peters proved the Kasten-Stigm threshold for sparse random geometric graph, sparse like soft random geometric graph. And they prove it to be equal to NP times lambda1 rho square. Lambda1 is some like Fourier coefficient. Well, some Fourier coefficient for the function rho. Okay, so maybe I'll just say quickly what this KS threshold really is computing. It's essentially computing like in this model, in the tree model, like if we're given a graph like a tree, what is the inner product between the root and a leaf? The expected inner product over the standard deviation between them. So I guess this has its origin in some other problems like community detection, where KS threshold correctly predicts the threshold for weak recovery for all those models, for distinguishing and recovery for those models. So I would see this as evidence that below this threshold, like below D is equal to n times p times lambda1 rho square, we'll be able to do recovery.
Question. So,
yeah.
I mean, what's I here? It's for some fixed I? The KS threshold, is it defined with respect to some fixed VI?
Not a fixed VI, but just any leaf, just one leaf.
Any leaf. Oh, okay. Okay.
Yeah, yeah, that's what I kind of mean. Just one of the leaf. Yeah.
Okay, thank you.
Oh, no problem. Yeah. So here's the thing. This is through like talking with experts in this field, with Schramm and Bangachev, that they told me that essentially recovery is efficient. We know that people believe or could even already prove using some existing technique that recovery is efficient in the random geometric graph when D is much smaller than NP. However, I was still unable to find a concrete reference, so I didn't put a citation here. But I do think this is actually true using some existing techniques. So I'm putting it here without a citation. So after I double check, I will try to put up a proper citation for this thing. So this is this is the recovery side of the question. So indeed, I think it confirms the KS intuition here. Okay, and also I learned that recovery is also information theoretically impossible when D is, oh, sorry, this is my bad. When D is much bigger than NP. Yeah, when D is much bigger. This is not smaller. This is wrong. It's much bigger than NP. So essentially, we know a tight threshold for recovery already. So yeah, so on the recovery side, the story is like more complete. Okay, so I guess I'm going to end early. So, but I will just conclude with some other like open questions in the direction of random geometric graphs. So first, of course, there's the open questions in which we already talked about, like the questions about trying to close the gap in the distinguishing problem. Closing the gap when, for what regime of D can we say that, can we know that information theoretically it's impossible to distinguish between Erdős-Rényi and the random geometric graph over unit sphere. But other than that, there are also many other interesting computational questions on these random geometric graphs I'm listing to here. And there are only partial results in these areas and many interesting open questions. In particular, people didn't figure out the threshold for these problems. So I think that's very cool directions to look into. One of the examples is dimension estimation. So in dimension estimation, what you get is you actually just get a graph, but you're not you know the graph is coming from, like, let's say a unit sphere. It's actually a random geometric graph coming from a unit sphere, but you're not told the dimension of the sphere. The question is, can you correctly estimate it with high probability? So that's one question. That's a dimension estimation question. There's also the manifold reconstruction question, in which you're given a random geometric graph. Now the question is to not just this is to essentially recover the entire metric among these points that's given. So this is a bit related to the recovery problem, but you can think more generally about this problem over other manifolds. Okay, so these are the two questions I want to mention, and I think that's it. And thank you for listening.
Thank you very much for the beautiful talk, Siqi. Let's thank everyone. Yeah, so we have lots of time for questions. So questions?
So for random geometric graphs on the sphere, so is there some sort of a way to get some sort of a random triangulation of the sphere from these random geometric graphs?
Random triangulation. I guess it depends on what you want from it. I guess one naive way, is you simply just take all the triangles in the appear in the graph, and that gives you something. But are you specifically looking at the triangulation for that specific dimension? Like, is there any additional property that's being looked for?
Yeah, like the only thing I have in mind that the triangulation that we get, that is implication complex that we get, it should be homeomorphic to the sphere.
Oh, that's a very good question. Yeah, okay, so actually I've thought a little bit about this, of trying to show like at least maybe like a homology behaves like somewhat similar to the to the sphere itself. I really think that's true, but and I can prove that for specific types of not just a random discretization of these spheres just by randomly sampling. One can prove things like that. But for random subsampling, I don't think I know how to prove that, although I do personally believe it's true. Like you can prove that homology of lower dimension should vanish. So yeah.
More questions?
So in the manifold reconstruction problem that you're mentioning, so what's the setup? So it's like some arbitrary manifold, but the points are on the manifold?
Yeah, okay, sorry. Can I go back? Oh no. Okay. Yeah, so a manifold reconstruction, so it actually comes from a manifold. But I guess the thing is you also know the threshold function. Like for example, you're in the soft model, you actually know the function rho. But you're asked to recover the distance between every pair of vertices in this graph.
So you you know the metric of the manifold and you want to find out the geodistributions on the manifold between the points. That's the
yes. So just between the vertices you have.
Okay, so the analogous thing is maybe so what's the analog in the sphere then? So in the sphere you have the points and
analog in the sphere
is the analog of finding the gram matrix. Is that correct?
Yes, that's correct, but in a stronger way is my understanding. Like, yeah.
Thanks.
No problem.
More questions? So I have just one curiosity, Siqi. So
yeah,
I think it's likely that in order to learn about, how you can leverage this toolkit to construct high-dimensional expanders, so to invite you again. But like any short glimpses, like any summary, is it possible? That how do you leverage this toolkit to produce high-dimensional expanders?
Yeah, actually, yeah, that's a very good question. So actually, already, we already see like these random geometric graph on the sphere would have many more triangles than like Erdős-Renyi graph of the same edge density. So that's kind of already intuition why that could potentially give high dimensional expander in which we actually required to have many more triangles to exist because of like we want local connectivity, what's so-called local connectivity. And a naive way is just we choose proper choice of dimension D and as small as possible choice of edge density P, so that actually we can get a high dimensional expander in which the neighbors of a vertex are also well connected. So that's something that's possible, although that doesn't give you bounded degree high dimensional expander, so that still requires pretty high degree. So I think, well, my personal feeling at this point is that probably it's better to think about deterministic ways of discretizing these manifolds from probably more algebraic tools that could potentially give much sparser results. I think random may not be the best way to achieve like very sparse bounded degree high dimensional expanders.
Thank you very much. So more questions? All right, so let's all thank Siqi again for staying up late in the night.
Thank you.